Alright, so a little exponential problem for you here. We are purchasing a Tesla Model S, um, and the car will depreciate in value by 11% each year, which means each year it will go down in value by 11%. So when we purchased this car new, it was 70 grand, and we want to know, based off of this depreciation, what will be the value of the car in 5 years. Well, if it goes down by 11% each year, that means that 89% remains this year. So if we take that initial $70,000 and we multiply that by the fraction 89 over 100, that would give us the depreciation after 1 year, but we want it after 5 years, so we're going to multiply by 89 over 105 times, which is raising that to the fifth power. So we can plug that into our calculator and get that the car is worth $39,088.42. But-choo! So let's just jump straight into what we're going to do today. We're going to look at some more half-life problems, and then we're going to look at some interesting quadratic stuff with exponential functions. It's cool, so let's jump into it. First off, niobium-94 has a half-life of 20,300 years. If 45 grams are present currently, how many grams will remain in 15,000 years? So we're going to use our PERT equation, as always, and let's think about what we know and what we need to find. We know that the half-life is 20,300, and so we need to use that to figure out the rate. And so if you were with us on the last video, we know we're going to be able to find that rate by taking the natural log of 1/2 and dividing it by the half-life, which is 20,300, and we can crunch that and get a value, and that value will be negative 3.415 times 10 to the negative fifth. I'm writing it in scientific notation because it's a teeny tiny number, but you should go ahead and store that as some variable. Call it R for rate. So store that value, and now we want to use that value to figure out the amount after 15,000 years. And so to do that, we know we have the initial population size of 45 grams. And using the PERT equation, 45 times e to the power of our rate, which is our stored variable, r, times time, which is 15,000. So plug and chug, and you should get 26.964 grams remain after 15,000 years. That's a long time. But now I want to think about something a little different, and we did this in the last video, but we'll do it again here. We're saying let H be the half-life of a radioactive isotope. Write the equation that represents the rate of decay in terms of H. Well, think about what we just did. We knew that we were going to get the natural log of 1/2 divided by the half-life would give us our rate. And now we want to take that rate and substitute it into the general PERT or poked equation and then simplify the inverses that pop up. So what I'm saying is we're going to take our equation, A of t equals P times E to the RT. But instead of R, I'm going to write the natural log of 1/2 divided by H. So there we have our PERT equation with a fancy R. Now we're going to simplify this a little bit and say this is the same as P times E to the natural log of 1/2 to the power of T over H. Just using some properties of exponents there, but notice what we have inside those parentheses. E to the natural log of 1/2 simplifies because e to the x and natural log of x are inverses. So we get P times 1/2 to the power of T divided by H. So we get this alternate form of an equation that allows us to solve half-life problems, which is pretty nifty. And sometimes this might be useful because if you think about it, we could answer that previous question without figuring out what the rate is. So if we use those same values and substitute in, we would get that the amount after 15,000 years is going to equal the initial population, which is 45, times 1/2 to the power of our time, which is 15,000, divided by the half-life, which is 20,300. So crunch these numbers, and again, you're going to get that same value, 26.964, and again, our units are grams. So let's use this on some new problems here. Problem number 1, if 80 grams of iodine are present initially, what percent will remain after 42 days? And we're told that the half-life is 60 days. So if 80 grams are present initially, we could set this equation and say that the amount at time t, but we know, amount of time t is 42. The amount remaining after 42 is equal to the initial quantity, which is 80, times 1/2 times our time, not times, but raised to the power of our time, which is 42, divided by our half-life, which is 60. But notice that this would give us not the percent, but the quantity. But let's run this number real quick and see what we get. We get 49.246 grams. And we need to answer this as a percent. So we need to take this answer and divide it by the starting quantity, which was 80. So we need to take our 49.246 and divide it by 80 to get our percent. And we get 61.557%. But think about a better way to do this problem. Since we ended up dividing by 80, well, imagine if we just hadn't put that initial quantity in there in the beginning. Then it would be like our starting quantity was 1, and then whatever answer we would get would already be a percent, because 1 is equivalent to 100%. So just like we've seen with the previous problems, if you're dealing with percents, all you have to do is not use a starting quantity, and then you get your answer in terms of percents. So question number 2, how long will it take until only 15% of a 30-gram sample remained? Well, let's think about what equation we're going to set up. We are going to say we want 15% to remain, so we're going to say 0.15 equals 1/2 to the power of our time, whatever it may be, that's what we're trying to find, divided by the half-life, which is 60. And so to get that t down, we need to use logs. So I am going to just take the log of both sides. And notice I'm just writing log, which means log base 10. You could do this in other logs. It totally doesn't matter. It's up to you. But I'm eventually going to be putting this in my calculator. So I'm going to say log of 0.15 equals log of 1/2 to the power of t over 60. And then we're going to plug it and get log of 0.15 equals log, I'm a liar, equals t, I can't write either, t over 60 times log of 1/2. And so we're going to get t by itself, and to do that we're going to get t equals, we need to multiply by 60 and divide by log of 1/2. So we're going to get 60 log of 0.15 divided by log of 1/2. And plug and chug at this point. And you should get 164.218 days until 30 grams has been reduced to 15% of that. But think about problem number 3. Problem number 3 is the same situation, but we want 15% of 90 grams. But here's the deal. It is going to be the same answer. Because think about how we solved that problem. We didn't do anything with the 30 grams. I mean, if we wanted to, we could be super careful about it, and we could use the formula as it's written and say that the starting size is 30 grams, but then the size after 60 days is going to be 15, or the size after T days is going to be 15% of 30 grams. So on this side, we have to have 30 times 0.15. So you see, we get 30 on both sides, and so we can divide by 30, and we get just the 0.15. So we could just as easily make that a 90 and a 90, and then we would still get just 0.15 over there. So, same answer. That's kind of cool. So, quick question for you to think about. Why does the following not make sense? Well, think about what this is saying. This is saying 3 to some power equals -4. Well, that is not possible, because if you think about what this exponent is saying take 3 and multiply it by itself x times. And you cannot multiply 3's together and get a negative number, no matter what you do. If you think about this literally as two functions, think about the function 3 to the x, which looks like that, and think about the function -4, which looks like that. Those two functions never intersect, so there is no solution there. So now we want to take this problem and we want to solve for x. And that may look pretty difficult, but notice that we have a log base 9 and log base 9, so it's probably going to be a good idea to combine those somehow. So I'm going to move this log over by subtracting it. So I'm going to get a log base 9 of 27x minus log base 9 of x squared plus 20 equals, we have this log base 4 of 2 over there. And that's saying 4 to what power equals, I don't want to write that as x, let's say 4 to the a equals 2. Well, what's the relationship there? Well, we need the square root of 4 equals 2, so a would have to equal 1/2. So I know this whole bit right there just equals 1/2. So now I am going to compress the left side to a single log, and I can take log base 9 of 27x divided by x squared plus 20. And that is, again, still equal to 1/2. Now I'm going to take this log and rewrite it as an exponent. So I'm going to say, as an exponential problem, I'm going to take 9, the base of the log, and raise that to the power of 1/2, and that is equal to 27x divided by x squared plus 20. And now 9 to the 1/2, that is just the same as the square root of 9, which is 3. Boo-doo-doo-doo, right there. And so I'm going to multiply this denominator up to write this in quadratic form, and I will get 3x squared plus 60 equals 27x. And now I have a quadratic, and so I want to solve this quadratic, and I will do that by factoring. So we'll rewrite this as 3x squared minus 27x plus 60 equals 0. I'm going to factor out a 3 to get x squared minus 27x plus 20. I am such a liar. Not 27 there, but 9, because 3 times -9 is -27. So we get that situation. And now, finally, sorry, I'm going all over the place. I'm going to factor that inside. I'm going to divide by 3 on both sides, because then I'll just get rid of that 3 and it won't make a difference. But I am going to factor that inside as x minus 5 times x plus 5 as such. And then using the zero product property, I lied again. I'm apparently a liar. It's now 10 and I'm starting to get tired. It's going to be x minus 5, x minus 4. I don't know why I said that. Boom, just like that. Because negative 5 times negative 4 is positive 20, and negative 5 minus 4 is negative 9. So that is how we factor that, and we get our two solutions, x equals 5 and x equals 4. Okay, similar problem here. We're going to end up with a quadratic again, and notice that all of these logs are log base 3. And so we want to go ahead and combine these, compress these to a single logarithm. So the first thing I'm going to do is I'm going to subtract 2 log base 3 of x from both sides. So let's make that a big minus sign, and we'll say equals 0 there. Now I'm going to compress this to get log base 3 of 7x plus 4. And then notice I have minus log base 3 of 2. So that's going to give me a 2 in the denominator there. And then I have minus 2 log base 3 of x. So if I unplug that, I will get an x squared there. And then I'm subtracting, so it needs to go in the denominator. So I get x squared. And the operation there in the middle between the 2 and the x is indeed multiplication. So I get this log equals 0. So I rewrite that again as an exponential problem and say 3 to the 0 equals 7x plus 4 divided by 2x squared. And 3 to the 0 is the same as 1, so I get this. And now I am going to multiply that up to get 7x plus 4 equals 2x squared. And now I will take this and rewrite it as 2x squared minus 7x minus 4 equals 0. And now I'm going to factor that. I'm going to get a 2x there, an x there, and I know my numbers have to multiply to negative 4. And so my only options are a 4 and 1 or 2 2's. 2 2's ain't going to cut it. So I am going to throw a 4 there, and I am going to throw a 1 there, make that negative, make that positive. And notice if I were to FOIL in, I'd get 2x times negative 4 is negative 8x. And I would get 1 times x is a positive 1x. So I get negative 8x plus 1x is negative 7x. And I would get 1 times negative 4 is negative 4. So I factor it like this, and I get two solutions. X equals negative 1/2, and x equals 4. But think about what we said on a couple slides ago. You can't have a negative value inside of a log, because then it gives you an equivalent exponential function that is undefined. So you can't do that. And if we were to use this solution of negative 1/2, well, think about this term right here. We would get log base 3 of negative 1/2. And so then that would be undefined, and we would not be able to solve this. So this is actually not a solution. But 4 is, so that is our one and only solution for this crazy log thing. Let's do one more of these things because they're fun. So we got this situation again, 2 log base 8s. Let's compress that to a single log base 8 of, I've got addition there, so I'm going to get x, I'm going to get this times this whole thing right there. So x times x is x squared plus 6 times x is 6x. That is equal to 4/3. Rewrite this as an exponential problem, and we will get 8 to the 4/3 equals x squared plus 6x. So now we need to figure out what 8 to the 4 thirds is. Well, remember what this is saying. This is saying take 8 and take the cube root of it, and then multiply it, or I keep saying that, and then raise it to the 4th power. Or equivalently, take 8 and raise it to the 4th power. I messed up. Take 8, raise it to the 4th power. Okay, I'm just messing everything up. Take 8, raise it to the 4th power, and then take the cube root of it. It doesn't matter which order you do it in, but we're doing this without a calculator, and which one of these is easier? Well, I don't know what 8 to the power of 4 is, but I do know that the cube root of 8 is 2. So I get 2 to the 4th, and then I know that 2 to the 4th is just 16. So I get 16 equals x squared plus 6x, and so I get x squared plus 6x minus 16. And so again, we want to factor this into two linear factors. So what two numbers multiply to negative 16 and add to 6? Well, that's going to be a positive 8 and a negative 2, because 8 times negative 2 is negative 16, and 8 minus 2 is 6. So we look at two potential solutions here, negative 8 and positive 2. But again, you got to think about the domain here. We cannot have a negative argument there. So that negative solution is not going to work, and our only solution is going to be x equals positive 2. So now let's solve this ugly thing. Notice that it is being described as quadratic type. And what that's saying is, notice that if we rewrite this, we have e to the x squared minus 3 times e to the x plus 2. So it's kind of like a quadratic equation. Like pretend, for example, we let e to the x equal some value t. Well, then we could say we have t squared minus 3t plus 2. And we could factor that as two linear factors. So what two numbers will multiply to 2 and give you negative 3? Well, that's negative 2 and negative 1. And so we get two solutions, t equals 2 and t equals 1. But think about what we said. We said t is e to the x. So really we have e to the x equals 2 and e to the x equals 1. So then what is x? Well, rewrite this as a log and get the natural log of 2 equals x, and the natural log of 1 equals x, which I can simplify without a calculator. Natural log of 1 is 0. Natural log of 2 I cannot simplify in my head, so I'm going to leave it as that. But these are two solutions to this quadratic thingamabobber here. Kind of cool. And here's another problem. We have a similar thing here, but it's a little bit uglier. So, let's see what we can do. It says rewrite it as a quadratic, kind of like that last one, so let's think about how we could do that. I'm going to get fancy here and say that 4 is the same as 2 times 2. Whoa, whoops. 2 times 2, and I still have that x there. And now then, think about rules of exponents. I could rewrite this like that. And well, look, I have 2 squared, and 2 squared is 4. So this is the same as 4 to the 2x, and then I could again be fancy and say that this is the same as 4 to the x squared minus 5 times 4 to the x minus 6 times log base 2 of 16, which let's figure out what that actually is. So let's figure out what log base 2 of 16 is. Well, that's saying 2 to what power gives you 16? Well, 2 to the 4th power gives you 16. So that thing right there is really just 4. So I have 6 times 4 is 24. So we're going to get a minus 24 over here, and all that equals 0. So again, let's think of this 4x as just kind of some term. So it's kind of like we have t squared minus 5t minus 24 equals 0. And let's find the values of t that make this equal to 0. So what are two numbers that multiply to negative 24 and add to negative 5? Well, we're going to get negative 8 and positive 3, because negative 8 times 3 is negative 24, and negative 8 plus 3 is negative 5. So I get two solutions, t equals 8 and t equals negative 3. And then remember that t is really a substitution for 4x, 4 to the x. So I get 4 to the x equals 8, and 4 to the x equals negative 3. We'll notice firstly that this right side will not have any solutions, because 4 to the x will never equal negative 3, thinking about the range of the function 4 to the x. And then look on the right, 4 to the x equals 8. Well, rewrite that as a log. We have, let me get my purple, we have the log base 4 of 8 equals x. And so I'm going to use change of base formula here and write this as log base 2 of 8 divided by log base 2 of 4. Notice where the 4 came from, notice where the 8 came from, and I chose the base of the log to be 2 because I know log base 2 of 8 is 3, and I know log base 2 of 4 is 2, because 2 to the second is 4, and 2 cubed is 8. So I get my solution of 3 halves. And I'm done.